All right, lastly, we have the example 4, our last spherical coordinate example. We're to integrate the function z over the region W. So our goal here is to find the triple integral over W z dv. And W is the solid region bounded between the elliptic cone x squared plus y squared equals z squared and a sphere of radius r centered at the origin. So for this problem in particular, I'm going to go ahead and just add on the stipulation that we're going to assume here that let's just pretend that these additional instructions were given, and z is greater than or equal to 0. Okay. Otherwise, this problem becomes a little bit more complex, which is not what I want to do right now. So let's just focus on the top half of this elliptic cone. So if we draw this region here, z-axis, our elliptic cone does this. So now an elliptic cone really also comes down and does it in both directions. But with this stipulation, we're going to just forget about that bottom half. So z-axis, x-axis, and y-axis. There's our elliptic cone. Since we're assuming z is greater than 0, I'm going to go ahead and solve this equation for z. And we'll choose the positive root since we want the upper half of the cone. So we can work with this instead. And we have a sphere of radius r centered at the origin. So this cone extends forever upward. It just keeps going upward. For that reason, I'm going to assume that since r is some finite number, I'm going to draw the sphere smaller than the cone. Because really, this cone does extend forever where the sphere doesn't. The sphere's radius is fixed at some value r. Sure, we don't know what it is, but it is fixed. And it is true, we actually don't have the full sphere, right? We only want the top half of the sphere. So more realistically, we have something like this. There we go. The top half of the sphere. Why the top half? Again, because of this condition. So the part that we're interested in is actually this. This sort of region here. Okay, so we can go ahead and blow that up and view that. Really, it's a cone, like a smaller cone. And since this portion is a sphere, we still have this little like spherical cap kind of thing. Something like that. And that's a sphere. Okay. So that's our region W here. It's this full region here. So this region here is essentially simple because if I start the origin, which is the tip right here, right? Same thing, the origin. If I start the origin and strike a straight line outward, the last surface it hits is the actual spherical cap. It doesn't hit a inner surface, and the last video example I mentioned that if when you strike your ray outward through your region, you only notice it hits an outer surface. Really what that means is your region must actually contain the origin. For if it didn't, that means it would have to pass through something to get into the region, right? So this contains the origin. So for that, we know that rho is going to be bounded below by 0 since our region contains the origin. So really, we know that rho is bounded below by 0. And then the outer surface is going to be the equation of this sphere. And since this sphere is radius r, the equation of a sphere in spherical coordinates of radius r is simply rho equals r. So our bounds for rho are 0 to r. What about phi? Oh, excuse me, phi, not theta, phi. For phi, clearly we start at the top, the z-axis, and imagine working our way downward this way, right? Phi is the angle from the positive z-axis downward. So the maximum we can go is whatever this angle is, wherever this cone is. Okay, so we start off at 0 because our region does contain, it touches the z-axis, and we need to know what this angle is now. To figure out that angle, there's a couple ways you can do it. What we did figure out last time in a previous problem that we did, so there's a couple options here. Option 1, you can just take this equation and convert it into spherical coordinates. So convert to spherical. Well, z is rho cosine phi. And in a previous example, we learned that x squared plus y squared turns into rho squared sine squared phi. Take the square root, you get rho sine phi, rho cosine phi. Rho's cancel. So what angle at what angle phi is the cosine of phi equal to the sine of phi? There's two locations where this happens. It happens here at pi over 4, because then you have root 2 over 2, root 2 over 2. And it happens again down here at 5 pi over 4, where you have negative root 2 and negative root 2. But since phi maximum range is 0 to pi, that means this 5 pi over 4 is outside our maximum range, so the only value of phi between 0 and pi, where this is true, is at pi over 4. So this tells you that this is only true in spherical coordinates if phi is pi over 4. So that's one way to get it. So phi is bounded above by pi over 4. Another way to do this is to think about, if you look at this cone directly in the YZ plane, so if you project it into the YZ plane, you basically just get this V shape. So what is the equation of the YZ plane? The equation of the YZ plane is, so I'm just going to say project into the YZ plane. It doesn't have to be this plane. You could also do it in the XZ plane, but since our perspective here is already sort of in the YZ plane, it makes sense to do it this way. If you project it into the YZ plane, you're going to take the equation of the elliptic cone and just set x equal to 0. So you get this. And the square root of y squared is the absolute value of y. And that makes sense because what does the absolute value of y look like? It's a v. So this makes sense. But also, if you were to draw this in the YZ plane, these are each a slope of 1. So a slope of 1 means a run of 1, therefore a rise of 1. Well, this is giving you a triangle that's a 45, 45, 90 triangle. So this angle here has to be pi over 4, and therefore this angle here has to be pi over 4. So no matter how you do it, you'll get the same thing. I think it's easier to think about this geometrically, so more option 2 than option 1, but some people really do like to do option 1. So that's up to you. So now that we have that, we want to think about theta. So for theta, does our cone, does our region, our solid region here, does it extend all the way around the z-axis? Yes, all the way around. So 0 to 2 pi. Once you have that, you can begin taking this integral here and converting it into spherical. So this would be the integral from 0 to 2 pi. the integral from 0 to pi over 4, integral from 0 to capital R, and then z is the in spherical coordinates, z is equal to rho cosine phi. And as a reminder, dv for spherical coordinates is rho squared sine phi d rho d phi d theta. So that's the integral setup, and for many of these, not all of them, but for a good number of them, we may ask you to just set up the integral, because as you all have now should have experienced and seen, setting up the integral is the harder task than integrating it. So at this point, we'll just leave it set up like that, and then there's some dots, and the answer here should be r to the 4th pi over 8. And that's the answer there. Okay, that's the last spherical coordinates example.